Okay, thanks. Welcome back, everybody, to the next part of our 40 years of elliptic curve cryptography celebration. It's my great pleasure to introduce Dan Bonnet from Stanford University, who is also an extremely distinguished and well-known researcher in the field. And he's going to be giving us an update on some of the unexpected applications of elliptic curves. So, Dan, the floor is yours.
Fantastic. Thank you so much, Stephen, and welcome everyone. Thank you both to Tanya and Stephen for running this celebration. I can't believe it's 40 years. It's kind of amazing to see everything that's happened in this area in the last 40 years. So yeah, glad to be a part of this, I guess, of this journey and of this event. I guess that what I wanted to talk about today is kind of the applications of elliptic curves, specifically the extra structure of elliptic curves, which is these pairings. That, as you all probably know, this has kind of become a whole world, and it's kind of impossible to cover this world in 30 minutes. So I'll just give a few highlights, and we'll see how it goes, and happy to take questions if there's time at the end. All right, so let's jump right in. So in the beginning, we had the projective line. Yeah, and the projective line enabled us to do a whole bunch of things, like Diffie-Hellman key exchange, public key encryption, digital signatures, some form of zero-knowledge proofs, lots and lots of amazing applications, and we were all happy, all was good. The problem was, of course, the projective line, or as we know it, discrete log in finite fields, is not particularly hard. In particular, there are sub-exponential attacks, which forces these primes to be quite large. So the next thing that happened, of course, is the development of elliptic curve cryptography by Victor and Neil. Amazing proposals at the time. I have to say, this is the reason why I started learning about elliptic curve cryptography, or elliptic curves in general, is because of the work of Victor and Neil. So this was an amazing opportunity for me. So thank you to both of you for introducing this technique and this idea into the field of cryptography. And of course, the point is that these are finite abelian groups of sufficiently large order. And the point of this is that discrete log appears to be much harder on an elliptic curve than it is on a finite field. Yeah, and because of this, elliptic curves scale better as we move to higher and higher security parameters, at least as far as we know, right? So we hope the problem is harder. Of course, we can't prove that it's harder, but it's been quite a few years, and it still seems to be much harder to do discrete log on elliptic curves than it is to do it on a finite field. By the way, I couldn't resist, and I had to put a reference to this book that I really liked, which is kind of tracing back the development of elliptic curve in general, elliptic curves as a mathematical discipline, all the way back to Diophantus, kind of through the ages. And in this book, Bashmakova actually kind of shows how the group operation was discovered over and over and over again. It seems to be independently over the last 2,000 years, and then finally stuck apparently in this work of Poincaré from 1901, and that's kind of where we get the group action on elliptic curves. So it's a really fun book to read. I highly recommend it. But even though initially elliptic curve cryptography was there for performance, yeah, we can use smaller parameters and still achieve the same level of security as we would get from a finite field. So the main motivation was performance. Magically, it turns out elliptic curves actually have an additional structure that enables a whole bunch of new applications in cryptography. Yeah, and that opened up a whole new world of things that we just couldn't do any other ways, right? So here I just have to remind you of what a pairing is. So we have a pairing. It's a function that takes 2 points or 2 group elements. One is in G1 and one is in G2, and then outputs a third group element that happens to live in what we call the target group, G sub T. And this pairing basically is a map that is a bilinear map. So I wrote down the bilinearity conditions. It also has to be non-degenerate. So we don't want to map everything to 1 because that's kind of trivial. And it has to be polynomial time computable. Yeah. So so the map is computable, and here I wrote what it means for it to be non-degenerate. Yeah, so that's a pairing. And of course, what's important for us is that the discrete log problem is hard in these groups, G1, G2, and GT, and that kind of makes it cryptographically interesting. What's interesting is the best examples for pairings that we have today actually come from these elliptic curves. So again, thank you to Neil and Victor that made this all possible. And the kind of examples we have today is where G1 and G2 are contained in certain subgroups of the elliptic curve. I guess one group lives over the base field, another group lives over an extension field for some small value of alpha, and the target group happens to be just roots of unity in the finite field. So again, if you're interested in the history of the veil pairing, actually Aline wrote this nice blog post that kind of traces back the history for when was the pairing defined and so on. It's an amazing story. Actually, apparently Veil came up with it during World War II, like in all the chaos that was happening in Europe during World War II. He did this amazing work, and along the way, he came up with this pairing, but he only wrote it up many years later. So it's kind of interesting to read the blog post to see kind of how things actually developed. But of course, the pairing by itself is not enough. We also have to make sure the pairing is computable. And for that, we have Victor to thank for, who came up with this, the famous Miller's algorithm for actually computing the pairing on elliptic curves. Actually, the algorithm does a bit more than just compute a pairing. It's kind of interesting that it will compute general functions or certain functions on the curve. And so there's kind of the algorithm does much more than just compute a pairing, which seems to be not as well exploited as one would expect. Interestingly, I think Victor also mentioned this in his talk. Even though he wrote the paper back in 1986, and actually I put a link in the paper in my presentation. If anybody wants the PDF, they can read the original paper back from 1986. I'm proud to say that it's actually the oldest file on my file system back to 1986, but it was sadly only published in 2004. And I think Victor tells the whole story about what it took to publish this paper. Very interesting commentary on how the academic system works in terms of publishing papers. Okay, so we have this pairing, yeah. So we have this group structure, this pairing that operates on these triples of groups, and the question is, what can we do with it? And as we said, there's like a million things we can do with it. One of the simplest examples that I like to give is actually a signature scheme. Yeah, so this is called the BLS signature scheme. That dates back to 2001. The signature scheme is really simple. The only thing we have to use in addition to a pairing is a hash function that maps messages to elements in the group G2. Okay, so we're going to use this hash function. And just to quickly remind you, I'm sure many of you know how the signature scheme works. Let me just quickly remind you. What we do is we choose a random element that's between 0 and the order of the group. We multiply our generator G1 by the secret key. That gives us the public key. And then to sign, what we'll do is we'll take our message, hash the message into G2. Yeah, our hash function hashes messages into G2. We multiply that by the secret key, and then we get a very short and simple signature out of this hashed message. Yeah, and the way we verify the signature is by a simple pairing equation, which I just wrote over here. Yeah, so evaluating the pairing effectively takes verifying the signature effectively takes two pairings. Yeah, so this is a very simple signature scheme. I'm sure many of you have seen it before. And it's not even that difficult to prove that it's secure. It's based on the security is based on what's called a co-CDH assumption, the co-computational Diffie-Hellman assumption in this product of groups. And if this assumption holds, then we can prove that the scheme is existentially unforgeable, at least if we assume that we're in the random oracle model. Yeah, and I wrote down what this co-CDH assumption is. The reason for the co is that we need the normal CDH assumption would only use AG1 and BG2. Here we need the value A both in G1 and in G2. So we call that a co-CDH assumption. Now, this is a nice and simple scheme. Yeah, it turns out, signatures are just a single group element. Verification is a simple equation. And surprisingly, the signature scheme already has lots and lots of interesting properties. The new property that makes it so interesting in the real world is what's called signature aggregation. Yeah, so what signature aggregation allows us to do is it allows us to take signatures on many different messages by many different public keys and compress them all into a single signature. Yeah, and the point is, if this single signature verifies under the vector of public keys and vector of messages, that convinces the verifier that, in fact, all the original messages were signed correspondingly under the corresponding public keys. Yeah, so this is called signature aggregation. It's a compression mechanism. It's something that we haven't quite seen or easy to build from other signature schemes. And because of this, BLS is actually used quite a bit in the blockchain space, where space is very expensive. And so compression mechanisms are actually quite useful. And that's why BLS is kind of adopted quite widely in the blockchain space. Now, there's lots and lots to say about how to aggregate securely. It turns out I could have given like a 2-hour lecture just about how to aggregate securely. There are many papers on that. If you want to see a modern treatment of how to aggregate securely, there's a paper that we wrote from 2018, or in our book, we cover it, actually kind of give a modern view of how to think of aggregation and how to do it securely. That's kind of almost half a chapter in the book. So there's lots and lots to say about that. But in the interest of time, I'm going to move forward. Okay. So now that we have like this very simple signature scheme where we need to hash messages in order to sign, the next question is, can we build a signature scheme that doesn't require hashing? Yeah, so why would we not want to hash a message? Well, there are lots of applications where what you actually want to do is prove knowledge of a signature. Yeah, so you want to prove that you have a message signature pair. And if you have to start hashing the messages, it turns out producing that proof is actually much less efficient, because now the proof system itself has to hash the message. So the question is there a way to build a signature scheme that's secure without actually appealing to a hash function? And it turns out that also can be done using a pairing. And let me show you how that works. So basically, the secret key here is now going to be two field elements. I'll denote them by alpha and beta. They're chosen at random. And then the public key is going to be the corresponding two group elements, Y and Z. These are just two elements in G2. Now, when we want to sign, you notice what we'll do is we'll choose a random field element R. We'll compute this field element here, which kind of has the message and R and alpha and beta in the denominator. And the point here is that the message M is not being hashed. It's used directly as a field element in the signing algorithm. And then we use that basically to multiply by our generator G1 of one of the groups. And that gives us a group element sigma. And the signature is now not just a group element, but rather just R and sigma. So one field element and one group element. Yeah, that's the whole signature. Very simple. Again, no hashing is required. And again, you can work it out for yourself. It's not that hard to see that with two pairings, it's actually not that difficult to verify the signature. One thing that's interesting is that these G1 and G2, this pairing here is fixed. So it could be actually be made part of the public key. So verifying the signature really only requires one pairing in this key. Okay, so that's kind of an example of signature schemes that don't require hashing. In fact, we have other examples like this, but there's a particular reason why I wanted to show you this scheme. And the reason is, what does it take to prove that a signature scheme like this is secure? And so it turns out we can actually prove security, but we have to make a much stronger assumption than computational Diffie-Hellman. In particular, we have to make this what's called a Q-type assumption. So we make this Q sub S BDH assumption. Q sub S here is the number of signature queries that the adversary makes to the number of signature queries it makes to the challenger. So Q sub S, in some sense, is the number of messages that are being signed using the secret key. And as long as this assumption is hard, then in fact, we can argue that the scheme is secure. So what is this assumption? This assumption is not as clean as computational Diffie-Hellman. This assumption basically gives the adversary a bunch of powers of a secret value, say the secret alpha. We give the adversary a bunch of powers multiplied by the group element, along with some other two elements. And the goal of the adversary is to compute this element in the target group. You can kind of see for yourself that just by naively using the pairing, you're not going to be able to compute this element. And the assumption is that there's really no efficient way to compute it. So under this assumption, the signature scheme actually can be proven secure. And again, the cute thing about the scheme is that we can sign without appealing to a hash function. And there are applications where hash functions are problematic. And so this is a scheme where you can use directly to sign the message without needing to hash it using a complicated hash function. Okay, so what can we say about what is interesting about this assumption is that it turns out to lead to other interesting objects. Okay, so first of all, I'll say that this structure here, where we take a field element and raise it to power and multiply that by the elliptic curve point, I'll call that a tower of powers. Yeah, so again, alpha is a field element, alpha squared is a field element, and we multiply these field elements by the elliptic curve point G1. So we get a bunch of elliptic curve points here. And again, this is called the tower of powers of elliptic curve points. Okay, good. This tower in the scheme here is used only in the security proof. And so this is something that kind of many schemes only use this tower in the security proof, but as we'll see in a minute, maybe we can get more power by actually using this tower in the scheme itself. One thing that I have to point out is this tower by itself is a little bit of a dangerous structure. There's this famous Brown-Galant-Cheon algorithm that actually speeds up the computation of alpha if you are not careful. So really, when you're using towers like this, it's either best to use curves that are not vulnerable to this attack. This has to do with factors of p-1 and p+1, or you can be aware of the attack and just make the curve a little bit bigger to compensate for this algorithm. Okay, so this we actually know how to deal with, and so let's assume for now this assumption is okay. Oh, I guess before we move on, I just couldn't resist, and I had to tell you a little bit about the prodigy and how we prove that the signature scheme is secure. It's kind of a cute proof. And so the way it works is it says, well, suppose we have a signature forger, we'll call the forger A. What we're going to do is we're going to build an algorithm B for breaking this BDH assumption. Yeah, so if the assumption is believed to be hard, the forger cannot be efficient. Yeah, that's kind of what we're trying to show. And the way this algorithm B is going to work, it's kind of interesting. It chooses a public with a very special property. It chooses this public key so that it knows a signature in every single message. Yeah. So no matter what message the adversary is asking the algorithm B to sign, the algorithm B has a signature on that message. Okay, so we can sign any message of our choice, which is kind of interesting because if algorithm B already knows a signature on every possible message, how is the forger going to help it in any way? Because the forger is just going to give it a forgery on some message, but algorithm B already has a signature on this message. So how does it help? And the answer is that the algorithm A, the adversary, doesn't know which signature the adversary has, the algorithm B has. And so when it forges a signature on a particular message, it will very high probability give us a different signature on the same message. So now all of a sudden in this bubble here, we have two signatures on the message M. One is the one that we know, and the other one is the one that the adversary gave us. And magically, it turns out these two signatures, the minute we have a bubble with two signatures in it, that allows us to solve the BDH problem, the Q BDH problem. And as a result of this, the reduction is actually very tight, and it's kind of a fun reduction to work out. So just I couldn't resist and had to tell you this story. But the next step is to say, well, now we have this concept of a tower of powers, and the question is, what else can we do with it? So it turns out if we allow the tower of powers to be a part of the scheme itself, so we publish it as part of the parameters of the scheme, all of a sudden that enables completely new capabilities. Yeah, and so let me show you a very exciting construction that uses this. It goes under the heading of what's called a functional commitment. Yeah, so functional commitments are interesting objects on their own right, but it turns out that the interest in functional commitments kind of exploded over the last decades because it turns out functional commitments are really useful for building succinct proof systems. Yeah, and in fact, what I'm going to show you is a tool that's often used to build very, very short proof systems that generate very, very short proofs. So let me explain what a functional commitment is. It's a very natural object. So what we do is, first of all, we're going to fix a family of functions. Yeah, and maybe to be concrete, I'll tell you the family of functions we're going to be interested in are basically univariate polynomials of bounded degree over some finite field. Okay, so that's a family of functions, but we can be abstract and just fix an arbitrary family of functions. Now, what the commitment scheme allows us to do is, first of all, we run some setup algorithm to generate some prover parameters and verifier parameters. And then what the scheme allows us to do is it lets us commit to a particular function in this function family. Okay, so there's a commit algorithm that will output a commitment string that commits this, is a commitment to this particular function. Now, what does it mean to have a commitment to a function? What it means is that later on, anyone can present a value x in the domain of the function, and the prover, the committer, can, of course, produce f of x, which we'll call y, and produce a proof that, in fact, proof pi, that, in fact, y is equal to f of x, where f is the committed function. Okay, so there's a verification algorithm that will take the commitment, will take the pre-image x, f of x, the purported f of x, and the proof, and decide whether this proof is a valid proof that y is equal to f of x or not. Yeah, so effectively committing to a function, we're committing to a function if we can later on open the function at any point in the domain and convince you that we opened the function correctly. So of course we have to define security more precisely, and the idea behind the security definition is to say that the committer can only open the commitment in a way that's consistent with some function f in the family. And so this basically, so here is the definition in a bit more detail. Let's just walk through it. It'll just take 10 seconds. So basically what this is saying is that we generate these parameters for the scheme, and now the adversary is given the prover parameters. He will generate some commitment and a bunch of openings of this commitment. You notice up to n openings of this commitment. And what the adversary should not be allowed to do is basically make it so that there is no function in the function family that's consistent with all the openings, even though the verification algorithm verified properly all the proofs. This should say pi I here, by the way, not pi. Yeah. And so if the adversary cannot do this, so it cannot create many openings and convince the verifier that all these openings are valid, even though there's no function that matches all these openings, that is something the adversary should not be able to do. Okay, so we call this function binding, and again, it's a very interesting and important property to study. Okay, so I hope this is clear. And so now we can specialize and say, well, suppose we want to commit to a polynomial of bounded degree, and it turns out the best way to commit to a polynomial of bounded degree actually is using a pairing. Yeah, this gives us the shortest possible proofs. Okay, so again, we're trying to build a commitment scheme for this family of functions. And so let me kind of show you the commitment scheme. The commitment scheme is, again, simple to describe. It's very, very elegant. It's called the KZG commitment scheme. Inventors, Kate et al. And so it's based on this one simple observation that says that that a polynomial satisfies f of u is equal to v. So the polynomial evaluates to v at the point u, if it so happens that when we look at this quotient here, f of x minus v divided by x minus v, this quotient has to be a polynomial. Yeah, if this is a polynomial, then it's not difficult to see that it must be the case that f of u is equal to v. And I couldn't resist another way to say this, of course, is that the polynomial f of x minus v is in the ideal generated by x minus u. Yeah, this is kind of an equivalent to the fact that the quotient happens to be a polynomial. Okay, so how do we use this lemma to build the commitment scheme to univariate polynomials? What we'll do is in our setup procedure, we'll generate a tower of powers. You can see this tower of powers whose degree is basically the degree of the polynomial. And then we'll also include as there are verification parameters, we'll also this value alpha times G2. Yeah, G2 is a generator of the second pairing group, G2. And that's going to be our verification parameters. So the verifier parameters are very short. The prover parameters are as big as the degree of the polynomial to which we're trying to commit. And in addition, remember, there's this alpha here that's kind of secret, and the setup algorithm has to generate alpha and then throw it away. In the world of blockchains, this alpha is sometimes called toxic waste because we have to get rid of it and make sure that nobody ever knows what this alpha is. Now, the way we commit is very simple. If you give me a polynomial of degree less than d, and you want me to commit to it, it's not difficult to see that basically you can compute the group element, which is f evaluated at a secret alpha times g1. And you can do this as a committer. You can do this without ever knowing what alpha is, and I just wrote down the equation of how to do that using the prover parameters. Okay, so this is our commitment to a function. It's a single group element, just f evaluated at a secret alpha times G1. Now, the way we do an evaluation is basically using the lemma that I just said. Yeah, so what we'll do is the evaluation is literally, the evaluation proof. Yeah, we tell you what V is. We'll tell you that f of u is equal to V. And the way we prove that f of u is equal to V is simply we evaluate this quotient polynomial that I defined over here at the secret point alpha times G1. And again, the committer can evaluate Q of alpha using the tower of powers. Yeah. Tower of powers lets you evaluate Q alpha times G1 without actually knowing what alpha is, and that allows you to generate this evaluation proof. So what's remarkable here is, again, the verifier parameters are really short, the evaluation proof is really short, And verification is also really short. To verify that the proof is correct, the verifier just checks this equality here. And the way it checks the equality is basically using the pairing. Again, I wrote down the expression of the pairing, but all this expression is doing is just verifying that this equality holds, given only the group elements that the verifier is given. Okay, so again, 2 pairings allow us to verify that the opening proof for the commitment is correct. Now, the scheme, again, can be shown to be function binding under the same QBDH assumption that I stated before. The assumption now, the Q value is dependent on the degree of the polynomial that we're proving, but with this, we get function binding for the polynomial. Okay, terrific. So this allows us to do to commit to a polynomial. There are a couple of comments I wanted to make. The first one is that there are many variations on KZG. One that I really like is called Dory. Dory avoids this toxic waste. So the public parameters and prover parameters and verifier parameters they don't contain any secrets. The cost for removing the toxic waste is that now the proof is not a single group element, but rather like order log D group element. So the proof is a little bit longer, still logarithmic, which is very impressive, but now there are no secrets that need to be stored or disposed of during setup. I should also mention this KZG method generalizes to multivariate polynomials. And basically the point is just to generalize the observation that evaluation amounts to proving inclusion in some ideal. And so the generalization just uses a slightly more complicated ideals. And as a result, the proof is going to be K group elements, where K is the number of variables in the polynomial we're trying to commit to. Yeah, so slightly bigger proofs, but it allows us to commit to multivariate polynomials. Again, there's enormous amount of work on trying to make this better and better. And I just wanted to mention there's a paper from this year called Mercury that shows how to use these ideas, but it's actually able to get constant size proofs that are quite fast to compute. Again, very, very, very elegant ideas using tensors. I put links here in the presentation. If you're interested, this is a very, very nice paper to read. Okay, so we have all these nice ways to commit to polynomials of various types using pairings. And you might ask me, well, what is this good for? So I already told you it's useful for proof systems. But in fact, let me just show you like a couple of immediate applications for this. Yeah, so first of all, if we wanted to commit to a set, so we have a set of n values, it's quite easy to do, because what we can do is we can build a polynomial that has these elements as its roots, simply commit to this polynomial. The commitment is just one group element. And later, if I want to prove to you that u is in S, I just prove to you that f of u is equal to 0. If I want to prove to you that u is not in S, I prove to you that f of u is not equal to 0. Yeah, so we get a very easy commitment to a set with inclusion and exclusion proofs. It's as simple as that. If I want to commit to a vector, what I'll do is I'll interpolate a polynomial that satisfies, g of I is equal to vi. I'll just commit to this polynomial, and later when I want to open one particular element in the set, I can just prove to you that the polynomial evaluates to v of I at the point I. Yeah, so trivially, from polynomial commitments, we get commitments to sets and commitments to vectors. And one thing I should point out is, again, this is kind of a cute exercise, that in fact, you can open many polynomials at many points using a single group element, using a single proof. So the minute you start talking about polynomial commitments, their openings actually batch up very nicely. Again, very cute tricks with polynomials that basically allow you to do many of these openings at once, so you don't have to kind of open one at a time. So like I said, this has been put to use to a great extent in the world of proof systems. There are many, many applications to these schemes. And again, in the spirit of what we're celebrating, I want to point out that kind of the most succinct constructions still use pairings to this state. Okay, so so all is good, everybody's happy. But unfortunately, after all this work, or rather, despite all this work happening, there's this looming threat of quantum computers, which has been discussed already. So let me just say that by 2035, we are supposed to move away from pre-quantum encryption. For signatures, this is not quite happening, but at least for encryption, we are supposed to move to post-quantum systems by 2035. And so the big challenge for our community is basically to show that we can build things that are post-quantum secure that are as good as the things that we get from pairings, and this is still an open problem. So can we build a signature scheme that's as performant as BLS, short, aggregatable, has an easy threshold, has a distributed key generation? In the post-quantum settings, we still don't know how to do that. It's quite remarkable. Same thing with KZG. Can we have polynomial commitments that have as short a proofs as the ones that we would get from pairings? We still don't know how to do this. So there's a wealth of open problems here that really the community has to solve in order to meet these challenges. And finally, I can't resist, and I'll stop after this, I can't resist and just mention my favorite open problem in the world, which is why do we have pairings, but we don't have anything more than pairings? And so the question is, can we get these multilinear maps? I wrote down the definition here of what is a multilinear map. Effectively, it's an n-linear map where the groups all have a hard discrete log problem. Even for n equals 3, this would already have amazing applications in cryptography. It's so frustrating to me that it's been, how long has it been now? It's been 23 years, I guess, since this concept came out, and we still don't have a good way to construct multilinear maps, even for n equals 3. I'm sure somehow, I'm almost convinced there's someone on the planet who knows the answer, and we just haven't found that person yet. So hopefully this is something that will resolve in the future. Okay, so thank you very much. This was a lot of fun to participate in this event, and I guess it's congratulations to the whole community for 40 years of elliptic curve cryptography. I can't believe it's already 40 years, and I'm looking forward to many, many years of elliptic curve cryptography in the future. So thank you all.
Thanks very much, Dan, for that brilliant overview of some of the really cool stuff that's been happened since. I mean, you literally just said you're looking forward to the next years of elliptic curve cryptography. So I'll start with the quantum thing. I mean, what's your view on the urgency of post-quantum, or do you think we've actually still got a good while left of classical crypto?
I see. That's, I guess, the question on everybody's minds, right? So maybe I'll say that when we talk about post-quantum, we can't talk about it as post-quantum. We have to separate it into encryption and everything else. Yeah. So this was already discussed before. When it comes to encryption, we have to worry about these harvest now, decrypt later attacks. HNDL attacks. And so for encryption, it's kind of important to start moving to post-quantum systems soon. For authentication, like signatures, the immediate threat is not quite there. Yeah, and in fact, the Google Chrome team, they're kind of famous for saying that they are not going to move to post-quantum certificates unless there's an immediate threat. Yeah, just because the shift to post-quantum certificates is so costly to them. And so I think we have time when it comes. So again, for encryption, we have to move quickly. For integrity mechanisms, I think there's still quite a bit of time. And so there's still room to use our beloved elliptic curves for at least for that purpose.
And the applications you were talking about, some of this blockchain stuff. I mean, obviously the signatures falls under that, but these functional commitments and those applications, are they also of the nature that they can be they're not so critical now?
What's interesting is the blockchain is an amazing honeypot for telling us if somebody had built a quantum computer. Yeah, once we see these particular coins, they're called Satoshi coins. If we ever see one of these Satoshi coins move, that's kind of an indication that maybe somebody has succeeded in building a large enough quantum computer. So they actually serve a pretty good purpose here. Now, I should say that much of the blockchain space is actually preparing for the world of post-quantum. Yeah, and because if we want to run the world economy on these kind of systems, obviously we have to prepare for worst case events, and so there is already starting to be a move towards post-quantum systems also in the blockchain space. It's just probably not as rapid as we see in the case of encryption decryption.
And related to that, I suppose, in the previous session, we talked a bit about whether lattices and isogenies had been studied enough the need for hybrid solutions so that you've kind of got a bit of a safety net. Do you want to make some remarks about your views on the maturity of post-quantum?
Oh yeah, no, I'm sure that I'll just repeat what was said before. I am a very strong proponent of hybrid deployments. There is a risk. There's a pre-quantum risk of all these systems, and we have actually seen a number of the NIST candidates, even some of the finalists, get broken using a pre-quantum attack, using just a classical attack. And as a result, my position is that we absolutely should deploy these in hybrids, in a hybrid mode, relying both on the existing systems that we have today and the post-quantum systems. And I guess I can use this also as an opportunity to encourage people to study the post-quantum security of the post-quantum systems. There is a bit of a fear, as happened, for example, last summer. There was a 2-week period where we thought, oh my God, there might be a quantum attack on one of the leading post-quantum candidates. Fortunately, that turned out to be false. But it does show that more people need to study the post-quantum security of these post-quantum candidates. So the problem is finding people who are proficient in quantum algorithms and proficient in these assumptions. The intersection is not very big. And so definitely there's a very desperate need for more people to study this. A bit of a plea maybe for our community to spend more effort on it.
So we need more sophisticated.
About that. Stephen, I should say one more thing about that. In that, so one could argue that it's a bit of a risk to go and study the post-quantum security of these assumptions because there's a good chance that you'll fail. But I do want to mention that there's this beautiful conference called CFail, which is exactly supposed to be about cryptographic failures. And so even if you try an approach and innovate a novel approach and you don't succeed in getting an attack, even just publishing in CFail, the fact that you tried this approach and it doesn't work, that's actually quite valuable to the community. So people know not to try it, or maybe they can build on what you did. So there's value, even if you fail to generate an attack, there's still value in the work.
Yeah, that's a very good point. And I don't know, we've got time to talk about the publication culture and cryptography these days. I mean, Neil alluded to it in his talk. Crypto in the 80s, you look back at the proceedings and there's kind of 5-10-page papers and they've all got a beautiful idea in them. And I've been on the crypto PC this year and you're reading 30-40-page technical papers and you're struggling to find where the idea is. I don't know if you've got any remarks on that, Dan, as someone in the middle of it all.
Yeah, it's been a little frustrating too. Obviously, something is obviously going to break at some point. But I think the basic fact is our community is growing. There are more people doing cryptography research, and as a result, there are more cryptography papers being published. So obviously, that puts more pressure on everybody, on committees, on paper writers, on readers, and everybody. I would view this as a success of the community, right? I mean, the fact that there are more people now who kind of view cryptography as exciting, I would celebrate that. It's a success of the field. Now, how to deal with the growth of the field? Every field has had to deal with this problem. Don't even get me started about what's happening in the world of machine learning, where just last year there were over 14,000 papers published. Yeah, and so every successful field has to deal with growing pains, and I'm pretty sure I think we'll work through it, just like any other field has worked through it. But obviously, growing pains are not always easy.
Okay, and one last question from the Zulip. This is actually from Tanya herself. Is there thinking back to the discovery of pairing crypto, and of course it wasn't just you; it was Antoine Zhu, and I also don't want to forget to mention Sakai Ogishi and Kasahara, who are also working on this area. But back to 2000 or so, is there anything you do differently if you were starting again now?
Oh, anything I do differently? I don't know. Work harder.
I think you're pretty hardworking, Dan.
I don't know. I mean, Honestly, my rule in life is learn something new every day, right? If a day where I learn nothing new is a bad day, so I try to learn something new every day. And I feel just extremely happy that I was able to be there in the early days, and kind of absorbing all these ideas was tremendous pleasure for me. And so yeah, I'm just happy to be a part of it.
Awesome. That's a great answer. Well, thanks very much, Dan. Beautiful talk, and really great to have you part of this event. I'll get you to stop sharing now.
Yes.
So we're going to move on to
Did I stop
talk by
sharing?
Kristen. So thanks. So Kristen apologizes profusely. Yeah, thanks, Dan. You can either stay in or log out. It's entirely up to you. Yeah, so Kristen apologizes very much for not being here in person. And we've got a pre-recorded video, and we can see if there's going to be questions afterwards. If not, well, if people have got any final questions they want to put in the Zulip, I'll see if I can handle them myself, or you can ask me questions or whatever. Anyway, so we're going to do stream a pre-recorded talk. And I also need to mention that there's an audio problem in the talk. So we had an issue with the audio, so the audio needed to be re-recorded. So we've got a pre-record, and it's not exactly what you might hope for, but anyway, it's still going to have Kristen giving us her thoughts on the 40 years of elliptic curve cryptography. So if I've done my job right, Tanya, it says playback has been disabled by the video owner. So we have a technical problem with the sharing. I'm getting you seen the error message? There's a what? I'm
Thrilled to be here to help celebrate 40 years of elliptic curve cryptography. Elliptic curve cryptography is very much tied up with my own personal history, and so it's a pleasure to look back and reflect on the 40-year history. In fact, I was very pleased to be a co-organizer and a host for the 25-year anniversary of Elliptic Curve Cryptography Conference, which we co-hosted at Microsoft Research. And I'm very thankful to the steering committee for ECC and specifically to Tanya Lange and Stephen Galbraith for inviting me to give this talk. So, elliptic curve cryptography played a very big part in my life because in 1999 I was hired to go to Microsoft Research to work on elliptic curve cryptography with Peter Montgomery. And in particular, Peter was a very close collaborator and colleague of mine for more than 10 years, and we focused intently on implementation of elliptic curve cryptography and commercial deployment. And it was finally deployed in 2005 in Windows Vista. So let me talk a little bit about that history. So Peter Montgomery is very well known for a number of things, but including he wrote the Big Num library, which was a multi-precision arithmetic library for Microsoft, which was used in our cryptography implementations. And he's well known also for Montgomery curves, y squared equals x cubed plus ax squared plus x. So curves of this form, one example of those is ECC 25519, which was introduced by Dan Bernstein in 2005. That curve is defined over a finite field FP, where P is 2 to the 255 minus 19. It's a pseudo-Mersenne prime, thus the name ECC 25519. And it's been widely deployed in many libraries and protocols using the Montgomery ladder. And Peter's also well known for efficient Montgomery multiplication. Now, the ECC 25519 was not being considered and deployed at that time in roughly 2000 to 2005 when I was working with Peter. And in fact, for those kind of pseudo-Mersenne primes, the reported ratio of the cost of inversion to multiplication was something like 80 to 1, because you could do very fast modular reduction with Mersenne or pseudo-Mersenne primes. Whereas Peter's implementation of the Montgomery multiplication and other fast inversion techniques that he had meant that at Microsoft Research, we had an implementation where the ratio of inversion to multiplication in the finite field for general primes was more like 5 to 1. So this actually indicated that it was a good idea to consider affine coordinates for elliptic curves instead of the typical weighted or weighted projective coordinates, because the weighted projective coordinate system gets away with no inversions for each elliptic curve operation, but at the cost of more multiplications. So actually, both for our elliptic curve implementation and later for our pairing implementation, pairing-based cryptography, we were able to use affine coordinates and use things like Peter's simultaneous inversion trick. And so we did a lot of work to both implement and improve, optimize the implementations for different architectures. In fact, for the not just for the Windows crypto API and the later the CNG, but also for the Windows CE, which was the embedded operating system at that time. So we wrote a number of papers, including papers with Kirsten Eisentrager, Mathieu Siet, Marc Joie, and Michael Nerig on all of these kinds of improvements for elliptic curves using affine coordinates. So it was an interesting experience working with all of the developers in the Windows crypto API team, and we were very proud to eventually get this elliptic curve crypto shipped in Windows Vista. I think it was largely because of the Suite B algorithms that came through and necessitated, it made it a requirement to actually support ECC for crypto for any government contractor. So that was the main thing that really made a difference and allowed us to ship ECC in Windows. And once it was deployed in Windows, it was easy to get it spread both to other products such as the Windows CE operating system and throughout the industry. So the crypto API was replaced by the CNG, which was released in 2005. And on a personal note, that was a great experience for me to have worked for years to build up the relationships across the company with developers and a lot of different product divisions, and then to have the technology and our elliptic curve crypto libraries eventually shipped in product was in 2005 was very exciting. So as you can see, elliptic curve crypto in Windows Vista included support for signature algorithms such as ECDSA and also for the elliptic curve Diffie-Hellman. So these were largely based on the Suite B algorithms requirements, and the standard at that time. I don't quite remember exactly the curves, but there were prime curves, binary curves, and Koblitz curves. And in this initial version, I know that we supported prime curves and not so much the binary and Koblitz curves. There were various concerns, including issues of security. But so using the prime curves that were standardized, I think the ones that were standardized in the IEEE P1363 document were the ones that we used. And so then it was also interesting working with developers for the Windows CE operating system. It was an early version of ARM, and we had some optimizations and improvements which worked for the type of architecture that they were supporting at that time. Overall, it was a very interesting experience to be working on the early deployment of elliptic curve cryptography. I can barely remember it now, actually, but there was quite a bit of cooperation across the industry. I have a quote here from the Red Hat customer portal, actually, which showed using that later they had support for the curve 25519 that was added to OpenSSL. That reminded me that we worked with developers from OpenSSL, and also remember working with Bouncy Castle at the time. They were developing a cryptography library for .NET that supported ECC. And it was the Microsoft .NET framework that that provided built-in support for ECC through those classes. So there was cooperation across the industry, companies including Certicom, where we were talking quite a bit about how to get elliptic curve cryptography deployed, and so it was eventually a great success to see it deployed widely and spread across the industry. So before moving on to the next part of my talk, where I'm going to move from talking about implementations of ECC to pairing-based cryptography, I just want to say that As a number theorist, it was also really fun to work on elliptic curve cryptography in that period because it raised a lot of other interesting questions, like, for example, generating curves over finite fields with prime order, which led me to work on complex multiplication for elliptic curves, and then actually complex multiplication for genus 2 curves as well, and higher dimensional abelian varieties. So it was a very fruitful area to work in for number theorists, including now starting to work on pairing-based cryptography. So you've heard a lot about pairing-based cryptography from Dan Bonnet's talk, and I'd like to just talk about a couple different applications of pairing-based cryptography that probably were not covered in his talk. So for one, so the BLS signatures, the elliptic curve-based BLS signatures, or Bonnet-Lin-Shaham signatures based on the VE pairing, or it could be one of the other pairings, like the Tate pairing, the 8 pairing, all these different optimizations of the essentially the VE pairing. But BLS signatures had a couple of really nice properties. So one was the fact that they were shorter. So that was one of the big motivations for adoption of BLS signatures. But a second aspect was that you compute the BLS signature and it's homomorphic in the sense that if you have 2 points on the elliptic curve and you take the pairing of the sum of those with some other point, that will be the same as in the target space, actually multiplying the pairing of each of those 2 points separately, taken with the third point. So that homomorphic property was important for applications, including we developed homomorphic signatures for network coding. So network coding was widely used for content distribution in peer-to-peer content distribution networks like BitTorrent. And the advantage of network coding, the way that peer-to-peer content distribution works is that many different peers will divide up some kind of like content, like a movie, to be distributed, and it'll be divided up into packets. But if each of the packets are just kind of sent randomly all around the network, then you can have a bottleneck waiting for kind of the last packet to arrive at any given peer. Whereas network coding, what it does is take a linear combination of all the different packets and spread those all around. So that's good for avoiding, kind of a bottleneck waiting for some particular piece of content. But the problem is it makes content pollution a lot easier because one, nefarious node, adversarial participant, can quickly spread garbage throughout the whole network by just polluting their linear combination of packets. So we needed some kind of measure to prevent this type of pollution attack, and the BLS signatures provided a really nice tool for this. So we can actually insist on packets to be valid. They need to have valid signatures, and the nice thing about the BLS signatures is that because they're homomorphic, they can be recombined, and they fit very well with the homomorphic property that is necessary for network coding. So this was written up here in this. You can find this in this Wikipedia article, and the original paper with Dennis Charles and Kamal Jain was appeared in the 40th anniversary annual conference on information sciences and systems. So this was an interesting application of the BLS signatures for peer-to-peer content distribution, and the interesting thing about this space was that the security relies on the hardness of inverting the V pairing. So that introduced kind of an interesting new hard problem into the space. So next I'd like to talk about another application, which is kind of interesting, probably not very well known. So the BLS signatures enabled a framework, a non-interactive zero-knowledge proof systems framework called the Groth-Sahai framework, which used pairing-based elliptic curve cryptos to enable, for example, anonymous credentials or privacy-preserving credentials, and then as an extension of that, also delegatable anonymous credentials. So Melissa Chase, who was a researcher in my group at Microsoft at the time, had worked on delegatable anonymous credentials. And we realized that this idea could be applied to enable privacy in the healthcare system in an interesting way. So I was working actually from starting around 2008 a lot on privacy in healthcare and interested in privacy of electronic medical records and encrypting medical data. But it was interesting to me that if we tried to keep the electronic medical records, private in the sense of the storage of people's private health data being encrypted, for example, or using things like later homomorphic encryption, there was still a problem that if you go to the doctor and you get some procedure and then the insurance company needs to be billed, they'll find out, what conditions you have and what procedure you have. And so I thought it would be much more compelling from a privacy standpoint if you could actually also protect your privacy from the insurance companies, because there's a lot of data available that you can see how much health data is aggregated and actually sold. And so I thought it would be nice to be able to protect the medical data kind of end to end. So the delegatable anonymous credentials can be applied in this setting because when you go to the doctor and they order some kinds of procedures or tests, so they need to get compensated for your visit, this can be enabled with a credential system, which is allows you to kind of delegate tokens to various other parties in the healthcare system so that they would be able to have valid tokens and the insurance company would be able to confirm that it should make the payments without knowing exactly what the procedures had been. So this was a paper with Melissa Chase that appeared in the Usenix 2010 HealthSec workshop, and it's also on ePrint. But of course, not very popular with the healthcare system and healthcare providers, of course, because in general they want to, collect this information. So it was never deployed that I know of, but it's an interesting and fun application. And it shows how elliptic curve cryptography can have a wide spread influence. So in the last part of my talk, I'd like to talk about the follow-up. With the advent of quantum computers and in the future when we have, full-scale quantum computers that are available, they will undermine the security of elliptic curve cryptography, to put it bluntly, to put it lightly. So the quantum threat is that there's polynomial time quantum algorithms for attacking elliptic curve crypto. And if M is the number of bits, so for example, like 256-bit ECC, if M equals 256, you can see that a quantum attack on ECC requires 360 m cubed time and 6 m qubits. And this is roughly according to the Prusalka estimates from 2004. In 2019, of a paper with Chris Svore, Martin Rutler, and Michael Narig, with a little bit more precise estimates of the exact number of Toffoli gates and things like that that's required to attack elliptic curve crypto. But it confirms the asymptotic estimates from Prusalka. So you can see that with m equals 256, you're looking at needing roughly 1,500 qubits on a quantum computer. So even with in comparison with RSA, where m would be roughly 2048 for roughly the same security level, you can see that 2 times 2048, you would need a 4,000 bit quantum computer and 4,000 qubits. And so the interesting thing is that while for classical attacks, one of the reasons for the adoption of ECC is because we didn't have sub-exponential attacks, so we could get away with a smaller bit size. And that was good for, efficiency. What happens when you move into the quantum world is that that smaller bit size translates into a lower threshold in terms of how large of a quantum computer you need in order to attack ECC. So it's kind of interesting. It flips the vulnerability from making it, less vulnerable to more vulnerable at the recommended bit lengths. So once we have, a full quantum computer at that size, the elliptic curve crypto systems will be broken, and that so that's reflected somewhat in the timeline for recommendations from, for example, NIST and NSA. So the Suite B algorithms came out in 2005 and recommended the use of elliptic curve cryptography with those parameter settings that I showed earlier, roughly m equals 256 or 384. But in 2016, the CNSA requirements came out and increased the minimum bit length for ECC from 256 to 384 and advised that it was no longer required to implement them. So in response, that NIST started a 5-year quantum crypto competition from 2017 to 2022, and there are a number of different hard math problems that were used as the foundation for the systems that were proposed. So roughly speaking, code-based cryptography, multivariate cryptographic systems, lattice-based cryptography, and even supersingular isogeny graphs. So the code-based cryptography was introduced by McLeish in 1978, multivariate cryptosystems by Matsumoto and Mai in 88. Hofstein, Pfeiffer, and Silverman introduced the lattice-based crypto with the Entru company in 96. And with Dennis Charles and Eyal Goren, we introduced supersingular isogeny graphs in 2005. So that's the only elliptic curve-based system. And so I'm just going to focus the rest of my talk on the supersingular isogeny graphs and the hard problem that those are based on. So we actually introduced these supersingular isogeny graphs at the 2005 NIST hash function competition. And the hard problem was to find paths between nodes in the supersingular isogeny graph. This is actually a problem that had been studied by Stephen Galbraith in a paper from 1999 with only a kind of exponential algorithms known for solving this problem. So it seemed like a good foundation for a whole collection of new crypto systems that we now call isogeny-based cryptography. So the basic idea at the time was that we wanted to use graphs. So think of a graph G as being given by the vertices V and the edges E. And in particular, we wanted to use K regular graphs, so K edges coming out of each node, and the graphs should be undirected. So you can go either way on each edge, and also wanted to have kind of optimal expansion properties. So as you walk around the graph, you should quickly get to kind of a uniformly random place on the graph. And we also wanted, obviously, to have no known routing algorithms for finding paths, which was the underlying hard problem. So it was fun to find this set of slides that I actually gave at the ECC 2006 conference, introducing these graphs and this application of elliptic curves. So this is different than ECC because you're not doing the Diffie-Hellman problem on a single elliptic curve. Instead, the vertices of the graph, each vertex is an isomorphism class of supersingular elliptic curves, mod P, and the curves are going to be defined over either FP or FP squared and labeled by their J invariants. The vertices of the graph can also be identified or thought of as maximal orders in a quaternion algebra by looking at the endomorphism ring of the supersingular elliptic curve. We know from the Eichler class number formula that the number of vertices in the graph is roughly P over 12. So in our initial proposal for the cryptographic hash function, we proposed P to be roughly 2 to the 256, so that with square root attacks, you get something like 128 bits of security. So the nodes of the graph, again, are isomorphism classes, FP bar isomorphism classes of supersingular elliptic curves, and then the edges will be isogenies, and that's where the isogenies come in. So isogenies are birational maps, from one elliptic curve to the next, so they can connect the nodes in the graph, and they have the property like in the separable case. So if the degree of the isogeny, the degree is the size of the kernel. So if L is usually taken to be the degree, L is often equal to 2. So as you can see, it's co-prime to the characteristic P, which is a very large prime. And so in that case, the isogenies are separable, and you can think of the isogeny as just being modding out by the kernel. And you get a L+1 regular graph, and the way that the hash function worked was that you can use an input to the hash function and divide it up into blocks. In this case, bit by bit, you could use it to walk around the graph with no backtracking. So no backtracking is allowed. So that was the hash function that we defined. It was written up in Science Magazine in 2008. So this is a picture of a graph with more than 200 nodes for a prime, which was somewhere around 2,500. And so it's just nice to have a picture of what you could also think of this as the Hecke graph. And it's got a lot of deep connections to number theory. So again, it was an example of working in elliptic curve cryptography, and the applications brought us to a lot of interesting questions in elliptic curve in number theory, actually, and including hardness of walking around on this graph of the supersingular isogeny graph. And we also worked on higher dimensional analogs in 2007, also with Charles and Goran. Published an analogous paper on the graphs that you get from super special abelian surfaces. There's a lot of related work in this area, including working on these graphs with level structure, alternate protocols, for example, one popular one called Seaside, due to Tanya Lange and her collaborators. Lots of follow-up work. Sorry, this slide is a little outdated, but on signatures, attacks, graph structure, the ski sign by Christophe Petit and his co-authors, and many other different directions. So I'm glad to get a chance to talk about elliptic curve cryptography in all of its glory over the last 40 years. So both the implementations and the extensions. And thank you so much for listening.
That's good. Just go for it. All right. So I'd like to thank Kristen for her talk, and again send her apologies that she wasn't able to join the call live. She's deeply apologetic for that. I'd like to thank all the speakers today, Neil and Victor and Dan and Kristen for their talks. I'm glad that this is going to be kept on YouTube. There'll be a small amount of editing to fix in some of the gaps. And I very much want to thank Tanya for her very extraordinary efforts to pull this thing together despite a number of challenges. So I think there was a suggestion that I answer questions. Obviously, if you've got questions about Kristen's talk, you can post them to the Zulip. She will check on them when she returns, or of course you could email her if you've got any particular questions about her talk. Dan and Tanya have mischievously posted a few questions for me in the Zulip. So I will attempt to answer them. So Dan Bernstein has asked, how many years do you think it'll be before current isogeny crypto systems are broken? I would just say that my personal philosophy that guides my research is that I assume everything is insecure, and that we just haven't had the right ideas yet. So, but I'm very bad at predictions. So I'm not going to make any prediction about whether Seaside or Ski Sign will fall first, or whether it will be classical or quantum or any of the above. Something I will say that I've said before is that I think group actions like Seaside, I think they're very interesting for more sophisticated protocols. I don't think we'll be using Seaside as just a basic Diffie-Hellman substitute. So I see the potential for Seaside a bit more like what we have with pairings. We use pairings for the things we can't do with basic Diffie-Hellman. They allow us to access higher functionalities like Dan was talking about. So I can see a place for Seaside or some version of isogeny-based group actions where the performance is kind of acceptable because you're doing something which is higher value and more complex. So that's why I still think it's very interesting to look at variants of Seaside, not because I actually think we'll be using it for TLS, but we'll be using it for post-quantum versions of some of the things that Dan was talking about. That's my only prediction I'm making there. And then Tanya's asking whether I should have invented isogeny-based crypto. And yeah, my regret was being actually very pessimistic. So I remember talking to Dennis Charles at some point about this, and David Zhao, and also Anton Stolbanov when he was doing this stuff, and they were coming up with, trying to do constructive things with isogenies. And actually, I was I was very pre-quantum in those days, and I didn't see the point in it. So I was never going to come up with a good idea because I was too busy not being at all concerned about Shor's algorithm. So that's my excuse. I'm not seeing any further questions in the Zoom. So I think we'll just wrap it up. So thanks for joining. I'm very happy that there was still a good number of people watching the live stream right to the end. I know it's very late in Europe. So thank you, everyone. See you all again in 10 years' time. And thanks again to Tanya. So that's it from me.